Okay, welcome ladies and gentlemen to section 1.4, dealing with what's called building functions from functions. We're going to be looking at composing two functions or compositions of functions. We're going to be looking at decomposing two functions or a function into multiple functions. We're going to look at something called implicit functions and these ideas called inverses. I'm going to start off with this quote, one of my favorite quotes of all time probably for mathematics. The only way to learn math is to do math. If you continually say, I can't do it and won't try, you're not going to get it and you will never get it. All right, so let's start off with compositions. A composition of two functions looks like f of g, or Fogg and Goff is what I usually call it. And you might remember this from Algebra 2. Fogg and Goff really looks like f of g of x, or g of f of x. And this is just taking the, in Fogg, f of g, this says take the function g and plug it into f, or take the function f and plug it into g for g of x. In the same sense of saying f of 3 says take the number 3 and plug it in place of x for the value, and usually you get some sort of number out of the function. So if I was to look at something like this, f of x is defined by the function 2x squared minus 1, and g of x is defined as x minus 2. If I wanted to find f of g and g of f, they're two separate questions. So let's just go ahead and start with f of g of x. That says take the function f and plug in the function g for every x value. So f looks like 2 times x squared. Excuse me. So we're going to take x. Well, in this case, it's g of x. So it's x minus 2 squared and then minus 1. So this is 2 quantity squared minus 1. Well, now we just have to simplify. This becomes 2 times x squared minus 4x plus 4, because you have to FOIL, minus 1. Simplify a little farther, distribute 2x squared minus 8x. I get a plus 8 and a minus 1, so I get a plus 7. And then the question is, should the other one come out the same? Well, let's just see. G of f of x. I'm going to take f of x and I'm going to plug it in for x in g of x. Well, g of x says take x, which is now 2x squared minus 1, and subtract 2 from it. And if I just simplified this, no foiling, no distributing, it's just 2x squared minus 1 minus 2, so minus 3. You notice you get two separate functions. The top one here is Fogg, or f of g. The bottom one is Goff, or g of f. This was called composition of two functions. So what I can do is I can decompose two functions, or I can decompose a single function into two separate functions that would look like a composition. So in my first example here, the one on the left, the y equals the square root of x squared plus 1, I can say if I wanted y to be f of g of x, I could say the outside function is the square root of x, and the inside function, or g of x, could be whatever's inside there. And if you notice, if I was to take g of x, x squared plus 1, and plug it into x here, into f of x, I would get the square root of x squared plus 1. This would be the decomposition of this particular function. Now there are more. We could have said f of x is equal to the square root of x plus 1, and g of x is equal to x squared. Those get the same exact thing. So notice we could change the things as much as we want. But normally, I'm going to write it as this. Likewise, for the second function, I could say the outside function is 1 over x, and the inside function is whatever this thing is in the denominator, x squared minus 2x plus 1. And again, that's obviously not the only thing we could have done. You could notice, and this one's a harder one, that x squared minus 2x plus 1 is actually x minus 1 squared. Which means this, if I wanted to, could be f of x being the outside function, could be 1 over x squared, and g of x could be x minus 1. So notice I'd plug in x minus 1, I'd square it, I'd get this denominator again. So again, two different ways I could have written this decomposition. All depends on which one you feel more comfortable with. Obviously, the first way is the easier one. Okay, moving forward, we're going to look at inverses. Inverses are pretty important in the study of math because inverses undo each other, like a square and a square root. They undo each other. Dividing by 3 and multiplying by 3, they're inverses of one another. They cancel each other out. However, we like to look at functions. So functions, if we were to try to find an inverse algebraically, what we're going to do is we're going to swap x and y in our equation. So you're going to have like a y equals blah, blah, blah. You're going to swap x and y right where they are, and you're going to resolve for y. And I have some examples here in just a few seconds. Let's get through all of our inverse stuff first, our definitions. In order for a graph to have an inverse as a function, we must use what's called the horizontal line test. You remember that this being a function, if we pass the vertical line test, it is a function. If it passes the horizontal line test, then its inverse is also a function. So here, notice it doesn't pass the horizontal line test. So the inverse of this function is not a function itself. But we can do some stuff to those functions to make inverse functions. Graphically, inverses are reflected across the line y equals x. So if you think about a cube function, looks like this. The cube root function, where's my pen color? The cube root function looks like this. So this is the cube root of x, and the red version is the cube of x. And it's reflected across the line y equals x. If you drew in the line y equals x right here, it's reflected across that line. And inverses are always reflected across the line y equals x. And what this basically says is if you have a coordinate x comma y in your original function, then the flip of that, y comma x, is in the inverse. So if you think about x cubed, the coordinate 2 comma 8 is on the function x cubed, whereas the coordinate 8 comma 2 is on the coordinate cube root of x. They're inverses of each other, so the opposite coordinates are on each other. And I did not mention this just yet, but I just gave you guys the symbology for inverse. Inverses look like this, f negative 1 x. We do not read this as f to the power of negative 1. This does not equal 1 over f of x. This is one of those areas in math where we use the same symbol for two different things. This -1 is not an exponent in our case. This means f inverse of x. So this is f inverse of x. Not an exponent of -1. You need to get that into your head now because we use inverses quite often coming up in trigonometry. All right, let's go ahead and, last little note there. Make sure you understand that the domain and the range swap because the x values in the function become the y values in the inverse. And the y values in the function become the x values in the inverse. So the domain and the range swap. So the domain of the function is the range of its inverse. In order to connect the two things for inverses and compositions, if f and g are inverses of one another, the composition of the two functions comes out to x. So if you compose the two functions, your answer simplifies down to x. And that works for both directions, f of g and g of f. So for our examples, what we want to do is we want to find f inverse and look at the domain of f inverse, including anything that we get from the original function. So let's look at that left function first. F of x is equal to x plus 3 over x minus 2. Remember, f of x is the same thing as y, so we're going to swap x and y. Then I have to somehow solve for y. Pay very close attention to this because I always get 1,000 questions on this particular question. This is technically a cross multiplication problem, so I get x times y minus 2 equals 1 times y plus 3. If I was to distribute this x, I get x, y minus 2x equals y plus 3. And since we are solving for y, I need all the y's on one side and everything else on the other. So I'm going to minus y, and I'm going to add 2x and add 2x. And if I do that, I get xy minus y equals 2x plus 3. And then if we look at this piece right here, both of these things have a y in them. So I can factor it out. I get x minus 1 equals 2x plus 3. And then this is just y times this thing, so I can divide by that thing. And I get y equals 2x plus 3 over x minus 1. And there we have our inverse. The domain of this inverse is x cannot be 1, and therefore it's negative infinity to 1, union 1 to infinity. But we have to pay attention here. X could not be 2 in the first place, so we have to limit that. We say x can't be 2 either from the original function. If we were to try the next question. Remember, this is a y, so I'm going to swap x and y. And I have to get y by itself. This is the easier problem. I'm going to square both sides. And I'm going to get y by itself. And I get that function right there. The domain here is all real numbers. But the domain actually comes from the range of the original function. And the range of the square root function was only 0 to infinity, oops. And since the range was just 0 to infinity, that's actually the new domain for this. So the domain here is not actually all real numbers. The domain is 0 to infinity because it's the original range from the function. Okay, let's keep going here. If I wanted to confirm these two are inverses of one another, all I have to do compose the two functions. So if I try to do f of g of x, so f of g of x is equal to 4x minus 3 plus 3 all over 4. And if I simplified this, I get 4x minus 3 plus 3 is 0 over 4. Cancel the 4's, I get x. Okay, so that works for that one. Now I need to try the other version. I need to do g of f of x. So I need to plug in x plus 3 over 4 into this function. So I get 4 times x plus 3 over 4 minus 3. 4's cancel. I get x plus 3 minus 3, which is equal to x. And there we go. Those two functions are inverses of another because they come out to x. This last little section here is our implicit functions. It's the word implicit we use a lot in calculus, so that's why I say it's a little taste of calculus. It's when you find two functions defined that gives a single relation. You'll see what I mean here in just a second. If I was to give you this first question here on the left here, you can't graph this in your calculator unless it's a y equals. So if we tried to solve for y, we'd say y squared equals 100 minus x, and then we would take square root, and we get this. Well, the problem is when you take the square root of both sides, you get a plus and a minus. So if we wanted to graph this in our calculator, we would actually have to write in both equations. These are the two functions defined implicitly by the given relation. These are implicit functions. Basically, they imply the original equation. Likewise, we can do the same thing on the other one. This one's a little bit harder. However, it is just a factored quadratic. X plus y times x plus y. I can square root both sides. So I get x plus y equals 1 and x plus y equals negative 1. I subtract x, I get y equals negative x plus 1 and y equals negative x minus 1. So this particular equation is two parallel lines even. So if you tried to graph this on your calculator, you would get two parallel lines. But these are the two functions implied or implicit functions defined by the original equation. Here is your assignment. Get working on that. I will see you guys tomorrow. Have a good evening.